Hello, everyone. The topic of my research is intelligent active and reactive power control using multi-layer neural network-based MPPT controller for grid-tied solar PV system under fault conditions. I am MATLAB from the Department of Electrical Engineering, Jamia Millia, Senior, India. The accelerating transition towards sustainable energy sources and the increasing deployment of renewable energy systems have transformed the dynamics of modern power grids. Among these renewable sources, grid-tied solar photovoltaic systems have emerged as a pivotal player in reducing carbon emissions and advancing green energy sustainability. Grid-tied photovoltaic system, which harvest solar energy and feed it straight into utility grid, offer a clean and effective way to generate electricity, but their smooth integration into the grid is not without its difficulties, especially when it comes to preserving system stability in the event of malfunctions. In any electricity distribution network, grid failure scenarios such as voltage swells, voltage sag, and short circuits are unavoidable. These type of disturbances have the potential to impair grid stability and negatively impact the performance of grid-tied photovoltaic installations. Grid-tied PV systems are required to adhere to diverse grid codes to ensure the stability of the system and strengthen its resilience in the event of disturbances. One of the key grid codes is low voltage write-through, or LVRT. The LVRT capability of the PV system involves staying connected to the grid despite a decrease in grid voltage magnitude. Simultaneously, the PV system should provide regulated reactive power injection to the point of common coupling to bolster grid voltage support. The previous research work focuses on LVRT performance of the grid-connected solar PV system under different faults and how the system can remain connected and support the grid, but did not adopt any intelligent technique for the MPPT along with the controller. In our research work, our controller is designed to work with neural network-based MPPT and to support the grid during balance fault as per the LVRT Indian Grid Code. The proposed system is able to stabilize the DC-link voltage as well as the oscillations in the active and reactive power under low voltage conditions. In the event of low voltage conditions on the grid side, the design system is able to deliver required amount of reactive power to the grid so as to stabilize the voltage level. As per the Indian Grid Code, the PV system should remain connected to the grid whenever there is voltage sag and supply reactive power to the grid till the voltage recovers or maximum of 300 millisecond, whichever is lower. Figure 1 shows the LVRT requirement in the Indian Grid Code. Inverter must remain connected to the grid above red line area, while below the red line area it should stop and disconnect itself from the grid. The reactive power injection requirement under different voltage sag levels is as shown in the figure 2. During fault, the injection of reactive and active current is given by equation 1 and 2 respectively. As per Indian Grid Code, the reactive current should be as per these equations. If the grid voltage is between 0.85 to 1.1 per unit, then the reactive current supplied from the inverter to the grid should be 0. On the other hand, the active current should be the rated current of the inverter in this range. When the grid voltage is between 0.5 to 0.85, then the reactive current should be supplied as K into 1 minus Vg into In, while the active current should be root of In square minus Iq square. In these equations, K is the adjustment factor, which is Iq by In by Vg, and it should be greater than or equal to 2 to provide proper voltage support under grid faults. Vg is the grid voltage level, and In is the rated current of the inverter. If grid voltage falls below 0.5 per unit, then reactive current should be the rated current of the inverter, while active current should be 0. In the LVRT operation, there are some challenges like during LVRT operation, under voltage sags, there is difference in the generated power and the delivered power of the PV system. Due to this mismatch, excess power gets accumulated in the DC link capacitor and it can result in an increase in voltage, potentially causing damage to the capacitor. To avoid this problem, in the proposed control technique, system is switched to non-MPPT mode during LVRT conditions so that power generation can be reduced. This is the design of the system. The system consists of 2 stages. First stage consists of DC-DC boost converter, which basically controls the power coming from the PV source. That is, it ensures that maximum power is delivered from the solar PV system under normal conditions and to provide proper control under voltage sag conditions during fault. The voltage source converter or voltage source inverter is on the second stage. The boost converter output is connected to the voltage source converter input through the DC link capacitor. The voltage source converter output is connected to the grid at point of common coupling through this LCL filter. The maximum power extraction ANN based algorithm is used for it. The grid current has harmonics, so LCL filter is used in the design to reduce the same. This is the schematic of the three-phase grid-connected PV system. The design parameters for the boost converter are calculated using these equations, and the parameters are like this. Input voltage is 230 to 350 volt, output voltage is 600 volt. Rated power is 100 kilowatt. Switching frequency is 5 kilohertz. So these are the parameters for the boost converter. The inverter data that we have taken is grid nominal RMS voltage line to line is 415 volt, grid nominal frequency is 50 Hz. Inverter side inductance we have taken as 500 microhenry. Grid side inductance for LCL filter is taken as 500 microhenry. Capacitance of the LCL filter is taken as 100 microfarad. Switching frequency of the inverter is 10 kilohertz. DC link capacitor is 3227 microfarad. DC link voltage is 600 volt. The flowchart of the proposed control approach is like this. First, the grid voltage is measured. If the grid voltage is below 0.85, then the active faulty mode of operation is activated. The required amount of reactive current is injected, and the DC converter controller is activated to protect the DC link capacitor from the excessive voltage. Once the faulty mode is cleared, then fault is cleared, then the faulty mode of operation is deactivated and the system comes back to the normal operation. In case the fault grid voltage is greater than 0.85, the system continues to work in the normal operation. The training data for the neural network is solar temperature and irradiation, for which 1000 data, one for each temperature and irradiation is generated for one set of samples. Output is MPPT voltage, which is further used to generate the duty ratio for the boost converter control. For training, temperature data varies from 15 to 35 degrees centigrade and irradiance ranges from 0 to 1000 watt per meter square. The training of the neural network is performed after determining the VMPP value at various irradiance and temperature level. This VMPP value is compared with the instantaneous VP generating an error signal that is fed to the PI controller. The output of the PI controller is then supplied to the PWM signal generator to produce the necessary duty cycle for the converter. Figure 7 shows the neural network training as done in the MATLAB. Levenberg math code is chosen for neural network because of its good convergence and stability. Performance is tested using MSE. These are the blocks which are generated after training. So figure A is the neural network block generated after training, and figure B represents the hidden layers inside the block. Figure 9 shows the regression data, and it can be seen clearly that all samples are aligned in the same line, indicating high accuracy in the data acquisition and confirming their validity. Figure 9b shows admissible mean square error, and it is 4.345 into 10 to the power minus 11 at epoch 1000. These are the results obtained from the trained neural network. It can be seen that the MPPT method is working properly and is able to track maximum power from the system under all varying weather conditions, with a maximum of 100 kilowatt, which is achieved when the irradiance is 1000 watt per meter square. Figure 11 shows the control logic diagram. Depending on the grid voltage, system switches from MPPT to non-MPPT mode. For DC link voltage control, PI controller is being used. In MPPT mode, only active current is fed from the inverter, while reactive current will be zero. The active current from the inverter is its rated value. In non-MPPT mode, the active and reactive current will be as per the level of drop in the grid voltage. In case grid voltage lies between 0.5 to 0.85, the active and reactive current will be fed as per the LVRT code. And if the grid voltage falls below 0.5, then that only reactive current will be fed from the inverter, and that will be the rated current of the inverter. Again, we have used PI controller in the current control loop with values of Kp and Ki given on the next slide. So these are the PI, Kp and Ki values for the voltage controller, and these are the Kp and Ki values for the current controller. To ensure feed-forward control, the voltage references are Vd star is Vt plus Rit plus Ldi by dt minus omega Liq. Vq star is Vq plus Riq plus Ldiq by dt minus omega Lit. The simulation results are obtained using MATLAB platform. There are two modes of operation for the implemented system depending on the grid voltage measured at the point of common coupling. One is the normal mode, which is also called as MPPT mode, and the other is faulty mode or non-MPPT mode or LVRT mode. In the normal mode of operation, that is when the grid voltage is greater than 0.85, and this mode system is generating maximum power as per the MPPT algorithm under varying radiation. Only the active current is fed from the inverter to the grid, while reactive current is zero in this case. These are the simulation results which are obtained in this case. We can see here, this is the PV power under varying radiations, and this is the active power from the proposed system. In the normal operation, we can see that when the radiation is 100 kilowatt, radiation is 100 kilowatt per meter square, 1000 watt per meter square, then the inverter output is 100 kilowatt. When the radiation is 600 watt per meter square, then the output of the inverter is 60 kilowatt. And when the radiance falls to 300 watt per meter square, then the output of the inverter is 30 kilowatt. The reactive power is 0 for the entire range of varying irradiance. PV output power we can see here. In the non-MPPT mode, this mode of operation is activated when the grid voltage falls below 0.85 per unit due to fault at point of common coupling. In this mode, system should operate as per the grid code and should supply active and reactive power depending on the drop in voltage level on the grid side. System performance is tested with fault simulation at the two instants. One is 0.2 second and the other 0.7 second. For this simulation, irradiations are kept at 1000 watt per meter square. Initially, system works under normal mode of operation and delivers maximum power as per the irradiation, and reactive power is 0. In this case, like here we can see, when fault occurs at 0.2 second, voltage drops to 180 volt line to line, which is less than 0.5 per unit. In this case, system promptly switches to non-MPPT mode so as to decrease power generation. The drop in power generation depends on the level of voltage sag. More voltage sag means more reduction in power. As per grid code, system should inject only reactive power. So we can see here only reactive power is injected from the grid in this case, from the inverter in this case. The transition from MPPT to non-MPPT mode is very rapid and stable. Figure 17 clearly shows that from 0.2 to 0.4 second, system is generating only reactive power while active power is 0. This fault persists for 196 millisecond. When fault is cleared at 0.4 second, system switches back to MPPT mode and the system is generating only the active power while the reactive power is 0. Since the voltage sag detection unit takes few milliseconds to access the grid condition, the MPPT and other control units continue to operate in normal mode instead of taking immediate action. Hence, there is a slight fluctuation in the grid current and in active and reactive power too. Another voltage sag occur at 0.7 second. During this, grid voltage drops to 270 volt, which is 0.67 per unit. That is greater than 0.5 per unit. So during this mode of operation, again the system is switched to non-MPPT mode, and the grid voltage, since it is greater than 0.5, then the system delivers both active and reactive power as per the grid code. So this condition continues till the fault is cleared and the system voltage regains back to the previous value. Once the fault is cleared, system comes back to the normal operation, and we can see here that it is just generating the active power, where reactive power is 0. DC link voltage variation during fault is found to be stable during fault when fault is cleared. Second, figure 19 shows that voltage and current are in phase during MPPT operation, and during non-MPPT mode, there is a phase difference between voltage and current from 0.2 to 0.4 seconds, since only the reactive current is fed from the inverter to the grid. The phase difference between voltage and current wave is 90 degree, while from 0.7 to 0.9, since there is a phase difference of less than 90 degree between voltage and current waveform, as inverter is generating both active and reactive current. Now we can conclude that as per the Indian Grid Code for LVRT condition, the design system is able to effectively perform under faulty conditions. Under normal operating conditions, PV system runs at unity power factor and it injects only active power, which is clear from the simulation results. ANN-based MPPT works effectively in delivering maximum power under all varying irradiations. During faulty conditions, system switches to non-MPPT mode and injects controlled reactive power as per Grid Code for LVRT. The DC link voltage is maintained constant and effectively controlled throughout the operation in the proposed control scheme. The proposed controller design for solar PV grid integrated system is thus effective under symmetrical voltage sag and enhancing the fault rate through capability of the system. In the future, system can be tested for other type of faults. These are the references for this research work. Thank you.